Well, hello. We're working on section 3.5 today, and 3.5, as you can see, is derivatives. Grab a pen here. Derivatives of trig functions. So we'll review those trig functions that we haven't done for a few months, and maybe learn something new, derivative called jerk. And I think we take a look at simple harmonic motion. So let's get the ball rolling. Quick little review. If I ask you if the sine of A equals -1, what is the cosine of A? Do you recall how this works? So if sine of A equals -1, then the sine inverse of -1 equals A. This is an angle that we're looking for, isn't it? And then I want to take the cosine of whatever A turns out to be. Unit circle, where is the sine equal to -1? Well, sine starts at 0 and goes through its classic period like that. It hits its highest point at 1, or of 1, at pi over 2, and it hits its least value of -1 at 3 pi over 2. Oh, we just found our A. Our A is 3 pi over 2. So what is the cosine of 3 pi over 2? Well, it equals 0. Goes to show us we need to know our unit circle. And that's just going to carry through again in BC, probably even more so than what we saw in AB. Tangent of A equals -1. What are two possible values for the sine of A? Okay, tangent of A equals -1. All right, so tangent, got to think about what tangent looks like. I'm looking for the erase button. Tangent, its graph is something like this, where we have dotted lines because we've got asymptotes at pi over 2 and 3 pi over 2. Whoops, not there. How about negative pi over 2? And it hits -1 about there. And that would be at negative pi over 4, wouldn't it? Yeah. So if I think about negative pi over 4, it also hits again at, let's see, I'm trying to think of how to draw this in there. Right there, this would be pi over 2 to 3 pi over 2, because it has a period of pi. And we're going to strike here again at what would be, 3 pi over 4. So I've got my two locations. I could word this differently. I could word it as 7 pi over 4. So what is the sine value of those two? Well, sine of 3 pi over 4 is root 2 over, tangent though, tangent. No, I'm right. We're going with sine. Sine of 3 pi over 4. Square root 2 over 2. And then if I'm at negative pi over 4 or 7 pi over 4, coming around the other way, I would be at negative root 2 over 2. So it looks like we're picking up two values on that one. The rest of them, number 9. I would love you to talk about number 9. So I'm going to pause you for a moment. Think about number 9. Equation of the tangent line to the curve y equals at the point 3,1. Everybody ought to be able to do this one. So here's my function. What am I trying to find? A tangent line. I think it's always a good idea to have a highlighter or a different color pen. Mark up your notes. That's kind of one of those avid strategies that we're trying to teach all students at HHS about. And then another important piece we've got to know at the point 3,1. So there's some critical pieces of information here. In order to get a tangent line, I need a derivative to get my slope. The derivative, f prime, I could have put y prime there. I just didn't look first. I get 6x squared minus 14x. I want to know the derivative at 3. So we're going to plug 3 in. We're going to get 54 minus, 14 times 3. I think 42 is what's coming in my head. Seems right. So I'm getting 12 as my slope. And then I got to write the equation. Y minus the y value, slope, times x minus 3. Done. Don't have to make it fancy, do we? A particle moves along a line with velocity for time t greater than or equal to 0. Find the acceleration. Do you recall how to get to acceleration? Well, there's that hierarchy, isn't there? We start with position function, then we go to velocity, and then we finish with acceleration, which is the second derivative. So if I had s, this would be s prime, this would be s double prime. So I am starting with velocity, and I got to go to acceleration. That's just a single derivative off of velocity. So I could say v prime is equal to a, which is equal to what? 6t squared minus 14. Minus 14. Oh, it was the same function as before. All right, v prime of 3, or a of, that's not good, which is equal to a of 3, would turn out to be 6 times 9 minus 14. Oh, duh. It's just like what we had done before, isn't it? I could call that 12. So I used it as a tangent line information, but it's also acceleration because we started what we called the function velocity. Sweet. All right. Reviewing our trig derivatives. The derivative of sine is cosine of x. The derivative of cosine is negative sine of x. And the derivative of tangent, one that people have a hard time remembering, is secant squared of x. The derivative of secant is secant x times the tangent of x. And cosecant, well, it starts with a c, and we remember that everything that starts with a c gets a negative for its derivative. So I'll have negative cosecant x times cotangent of x. And finally, for cotangent, it's kind of like secant, and that puts us at negative, because it starts with a c, negative cosecant squared of x. So commit those to memory once again. Just have to refresh, don't you? So the first one says find the derivative y equals x secant x. Whew, that looks like a product rule, doesn't it? Okay, so we're going to apply the product rule because we can see that we got two things multiplied. So we're going to enforce the good old product rule, f prime g plus g prime f. So I'll have y prime, always start with that left side. Derivative of x is going to be simply 1 times secant x plus derivative of secant x is secant x tangent x multiplied by the first factor, which is x. I'm going to put it in front because it would look funny kind of out there by itself. So it looks better to me to be in front. It won't get ignored as easily. You are essentially done with this derivative. I do say one nice thing that I could do. I could pull out the GCF of secant x, leaving me 1 plus x tangent x. And it's just good to be nimble with your algebra so that you can see those reducing or pulling out that can be helpful for canceling later on. All right, the number 2 says take the derivative, right? This means derivative with respect to x. The derivative of what? Well, here's our function. The derivative of sine x over cosine x minus 2. Fraction bar means quotient, which means quotient rule. So we're going to activate the quotient rule. And do you recall it? F prime g minus g prime f over g squared. So you could write dy dx equals, that would be appropriate. You could have written y prime equals, you could go f prime, just something that shows this is a derivative. Derivative is equal, derivative of sine is cosine x times cosine x minus 2. And then it's a subtraction. Now I take the derivative of the bottom, which happens to be a negative sine x multiplied by the top, which is sine x, divided by the bottom squared, cosine of x minus 2 quantity squared. Now, let's see, is there any simplifying? Well, if I distribute, I'm going to get a cosine squared x minus a 2 cosine x minus sine squared x. The minus part. I was hoping to get cosine squared plus sine squared, which could simplify to 1, but that's not what happened. So it looks like there really was no reason to simplify it other than it looks a little more concise. Simple harmonic motion. The motion of like a weight bobbing up and down on the end of a spring is an example of simple harmonic motion. And our problem says a weight hanging from a spring bobs up and down with position function s equals 3 sine t, where s is measured in meters and t in seconds. What are its velocity, acceleration, and jerk at time t? Well, jerk is a new one for us. Our AB course did not cover jerk, but jerk is really that sudden change in acceleration. So like when you put down the accelerator, it's the change of acceleration, right? Because it's the next derivative off of acceleration. So when you ride in a car or a bus, when it's jerky, it's not that the accelerations involved are necessarily large, but it's the change in the acceleration that is abrupt. Jerk is what spills your soft drink, like when you're in the car and you step it down, or maybe you put on the brake and you change your acceleration. The derivative responsible for jerk is the third derivative of the position function. So position, velocity, acceleration, jerk. And I'm going to try, I'm not sure this will work, but I'm going to try and activate this video. And it is going to play.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 44. It's on simple harmonic motion.
Okay, it's not loving me. I think I'll post the link and you can watch it later, okay? All right, so if we got to find jerk, we got to do some derivative work here. And it should be fairly simple, shouldn't it? Let's start off with s of t, our position function. And s of t is equal to 3 sine of t. Next, s prime, which gets us to velocity, I'm going to write v of t, would be the derivative of sine is cosine, isn't it? So we have 3 cosine of t. Take another derivative. So s double prime gets us to acceleration, a of t. And derivative of cosine is negative sine, so I'm going to have negative 3 sine of t. And finally, the third derivative gets us to jerk. I'm just going to do j of t is equal to negative 3 cosine of t. Interesting. That wasn't too hard. And they didn't really ask us at any specific time. So we got them all. Now, what would happen if I did a fourth derivative? Let's just do it. S of 4. Usually this should be, it's supposed to be a 4 there. S of 4 of t. When you get past the third derivative, the tick marks are going to get somewhat difficult to see. Sorry about that. And so we start labeling the derivatives with their number, like 4th, 5th, 6th, and you just put them in parentheses. So that's what I did there. And if I take the derivative, I'm going to be back to 3 sine of t. Do you notice something? There's a cycle to these derivatives, right? I'm kind of right back to where I started. And I could bounce through them. and then I'd be back to where I started. So yeah, sine and cosine do that. They have a cyclical pattern to them. Small group work, I want you to work on let f of x equal 6 cosine x to find the equation of the tangent line to the graph of f where the slope of f has a slope of 3 and a positive y-intercept. That will help us decide what point it's going through. This should be a huge clue as to how to find something like the x value. So take a moment, hit pause. This is a tough problem, but I know you can do it. All right, we are back, and I want you to do this problem, okay? So I'm going to have f prime of x equals, derivative, this is going to be negative 6 sine of x. And we want to have a slope of 3. So 3 is equal to our f prime, which means 3 is equal to negative 6 sine x. That's negative 1/2 equals sine x. And we can go sine inverse of negative 1/2 equals x. So now you need to think, where is sine equal to negative 1/2 on the unit circle? And on the unit circle, sine is equal to negative 1/2 at x equals 7 pi over 6, as well as come around the other side, 11 pi over 6. So there's our x value. Be one of those two, couldn't it? I want to find the y value. And the y value would be f of 7 pi over 6, which would be 6 cosine of 7 pi over 6. And that would be equal to 6. 7 pi over 6 for cosine is root 3 over 2. And that would give us 3 root 3. Oh, positive or negative? 7 pi over 6 would be negative. Let's get a negative on there. All right. Then, what if it were 11 pi over 6? If it were 11 pi over 6, oops, put the 11 before the pi maybe, we would have positive 3 root 3 because we'd be in quadrant 4, right? And that is an ordered pair. Now, I need my line, find an equation of the tangent line to the graph of f with a slope of 3 and a positive y-intercept. So I think they want our tangent line to have a slope of 3, so the derivative is 3, and it's got to be able to go through a positive y-intercept. So I'm just looking at potentials here, and 7 pi over 6 would have negative 3 root 3. But 7 pi over 6 could be written as negative pi over 6, couldn't it? No, it couldn't. 11 pi over 6 could be. Then it had root 3 over 3. Would it be, this is 7 pi over 6. I'm going to do some work on that one. Hang on a moment, because this one's got me baffled a bit. Okay, I am going to go with the 11 pi over 6 because of thinking of 11 pi over 6 is negative pi over 6. And if I had plotted negative pi over 6 and some other value, root 3 over 3, maybe I'm up in here, and then that would have a y-intercept that is positive. I was getting confused because I was thinking it was going to be a small intercept, but I just randomly drew that line. So we are good there. So my ordered pair I'm keeping is negative, oops, get a pen that writes, negative pi over 6, comma, root 3 over 2. And then I'm going to have the equation. Yep, find the equation of the tangent line. Y minus root 3 over 2 equals, whoops, I wrote this wrong, didn't I? This should have been 3 root 3. Sorry about that. So update this. 3 root 3 equals the slope, which was 3. Oh, yeah, that's right, because we set it equal to 3. 3x minus, I'm sorry, I got interrupted in the middle of this, and I'm trying to remember, it was like a long interruption, remembering where I was at, and then minus negative pi over 6. So that becomes a plus. Then we have our equation of the tangent line. Got it. All right. Next problem is fun too. Wanted to bring back though a recall on some of those trig things that we learned in pre-calc, like sine squared plus cosine squared equals 1. The special trig limit, the limit as x goes to 0 of sine x over x, that's equal to 1. This also can be flipped over, so we have x over sine x. And then the limit as x goes to 0 of 1 minus cosine x over x is 0. Those three are good things to remember for the test. Find constants a and b such that the function y equals a sine x plus b cosine x satisfies the differential equation. I think I'm going to let you work on that one, and I'm going to make just a separate video on that since this is getting long. And homework assignment is a WebAssign tonight, so we need to be signed up for WebAssign. It's 3.5. It's called 3.5 Trig Derivatives. So I have you loaded in WebAssign. If you remember your password from last year, it is the same, and your logon is the same too. All right. Have a fantastic day, guys. Oh, why is that not recorded?